Hey guys, welcome back to the Mystic Tech. In this video, we are going to manipulate some bits, sit back and let's enjoy. So in this particular exercise, we are writing the function that means the binary representation of a number, and the name of our function right here is convert to bin, which we are passing 12 as an argument to it. This is our function, our convert to bin function, and it's going to receive the argument with this parameter int num. Now let's proceed. First thing we need to do, since the maximum number of bits a particular integer can store is 32, then we need to use that to read all the bits in our number. We use for loop to do that, which will actually automate the reading. We say bit is what our bit is should be 31. The reason why we are making the bit 31 is because the maximum number of bits is actually 2, but that does not include 0. But in this case, while we are reading it, we want to include 0, so it's going to be 31. 31 with 0 is going to be 32, so we are making it 31. And while bit is greater than or equal to 0, then our bit decremented. We are decrementing the number of the bits, and for every iteration of our bit, we want to check the actual bits. We want to check if it's actually 0 or 1. We want to check if we've gotten to the first leading one. Okay, what do I mean with first leading 0? Let's assume this is our, I don't know the number of this, but let's assume this is 32 bits and this is the number which represents 12. Now we want to start reading from the first bit, and we don't want to print all the 0 till we get to the first one. We want to start printing from here to the last bit. So now we want to check if we've gotten to the first one. We say leading 0. Our leading 0 should be 1. We are doing something. We want to check the number. We want to check the bits if it's 0 or 1, and this is how we are doing it. This may not make sense to you. I recommend you watch the previous video, but I'm still going to explain it. This is num, right? And let's say the num is 12. The num is actually 12 in this case, and let's say this is the binary representation of 12. Now we want to right shift the num to the right side. We want to right shift it in number of bits position, and in the first iteration our bit is 31, and if this is 32, so we want to right shift it in 31 places. So it's going to shift all these other bits toward the right space, leaving us with the first one, and the first one is going to get compared with 1, and this is AND operator. So 0 and 1 is going to give us 0, right? So if 0 and 1 gives us 0, definitely the if statement will not get evaluated. But if let's assume we have 1 right here, and 1 and 1 will give us 1, then we want to print 1. So we want to print 1, and we want to print 1, yes. So that is if we have 1 right here, but if we don't, so the 1 will not get printed because our if statement will be evaluated to false. Then we'll continue with our for loop to read the next bit, and the for loop would continue until we reach where the first 1 bit is started from. Then we'll print 1, and we assign leading 0 to be 0. Definitely that will indicate that we've started from the first 1 bit, because we don't want to print all these previous bits which are 0. This will indicate our leading 0 to be 1. But what if we encounter 0 after the first one? So as if we don't, our leading 0 is 0, because once we start reading it right from the first 1 bit, then our leading 0 will get evaluated to 0. So else if our leading 0 is actually 0, then we want to print we want to put car 0. We want to print 0, then that's all. So we'll print 0, and if the number passed to the function, so our function is 0, definitely nothing will get printed because this for loop will not even get evaluated. Then we want to print 0 because our leading 0 will be 1. If leading 0, then we want to print 0, then our leading 0 will be 1 because the statement will not get evaluated. Then our leading 0 will be 1 right from the here. So our if statement will get evaluated, and let's check if our function okay. Let's see the error message. Expected okay on line 8. It's expected semicolon before. Okay, let's check again. B undeclared. Oh, 12 is actually 110. Let's check for another integer file. Let's see 23 exactly. So we wouldn't want to print all those previous zeros, so it's just the actually binary number. So let's move to the next exercise. In this exercise, we want to write a function that sets the value of a bit to 1 at a given index. The number is actually 1024, and this is the calling of our function. We are passing the address of this number and the index at which we want to flip the bit to 1, and we are printing the number. And here we are printing the number using printf. This is our function. First, we start by declaration of an integer. Let's say unsigned int I, and this I will be equal to 1 shifted to the position we want to flip, and we want to access the actual number by dereferencing the pointer, and we want to access the actual number and store the flipped value to the address in the memory, and then we want to return nothing. Let's just return 0. Okay, let's go through this. Let's discuss about this. First of all, we declare an unsigned integer variable, and in the next line, this integer I is equal to 1 left shift to the position. Okay, what does that mean? Let's say we have 1024. Let's say 1024 is equal to this. I'm actually just using this as an example. Okay, let's say this is 32-bit and you want to access the 5th bit of it, and you want to flip it to what? To 1. Then if we are flipping it to 1, what we are actually doing here is that we are pushing 1, we are left shifting 1 to the actual position. This is position 0, this is position 1, position 2, position 3, position 4, position 5. This is position 5 where we want to actually flip to 1. So now we are pushing 1 to that position 5. Let's push it to position 5 right from the okay, 1 is actually here, so we are pushing 1 to position 5 by having enough 0 behind it. So this is how to look like. So we have 50 behind 1. That means we are pushing 1 to position 5. Now that we've pushed 1 to the position that we want to flip, we are now storing the actual number into I. This means that this particular bit means something, can be converted to an integer, and the integer representation of this bit is 32. So we are now storing the 32 inside the unsigned integer. We are storing 32 inside this. So 32, we are dereferencing the pointer because the pointer is actually pointing to the address where this num is stored in the memory. When we dereference the pointer, we are accessing the actual number. So this asterisk PTR means we are accessing this number. It's still the same thing with we saying num is equal to num or I. Yeah, this is the meaning. We are saying num is equal to num or I because we are dereferencing the pointer, means we are accessing the actual value where the pointer is pointing to. So now num or I is going to be what? Odd operators takes 2 bits at a time and evaluates them one after the other. 0 or 0 is 0, 1 or 1 is 1. All these are going to be exactly the way they are when we OR it. But when we OR 1 or 0 is going to be 1. Definitely this particular 0 is going to get changed to 1 because OR or 1 is going to be 1. So at the end of the day, we will have something like this. We'll have something like this. We'll have something like this. So this 1 is going to become 1 and not 0. This is what we will have because it has been flipped to 1. So I hope you understand this, and let's check the new value. I hope you understand. Now let's check the new value. 1056. We are actually correct. So let's move to the next exercise. In this exercise, we want to write a function that sets the value of a bit to 0 at given index. Definitely, if you are setting the value of bit to 0 at a given index, if that value is already 1, it will get flipped to 0, and if it's 0 already, it will still be 0. So this is our function calling clear bit, and we are passing the address of the number and the index at which we want to flip the value to 0. This is our function. We have an integer pointer and we have an integer variable that's going to store the index, which is position, and the pointer is going to point to the address where the number is stored in the memory. Now let's start by writing the content of our function. We start by declaration of a variable, let's say unsigned int I, and in the next step we want to store the actual place we want to flip into the I using the bit operation. Let's say I want to push 1, I want to left push 1 to the position, and we want to check if the bit at that particular position is 1 already. If it's 1 already, then we want to flip it. If it's 1, then we want to flip it and restore it. We are done. Now let's explain how we come about this. We start with I equal to 1 right shift position. What does this mean? We want to shift 1 to the position where we want to flip. If the position is actually 5, definitely we are shifting 1 to the position 5. Let's assume this is the binary representation of 1024 and we have 1 and we have 1. If we are shifting 1 towards left, if we are left shifting 1 to position 5, definitely we have 5 bits at the end of the 1, at the end of our 1, and it's going to look like something like this. Yes, so it's going to look like something like this. So we have left shift 1 by 5 positions in 5 steps. Then we have 1 at this particular position and we want to flip it. So we are storing, if we are right shifting 1, this particular bit will be actually equal to something. Since this is actually equal to something, definitely the same thing applicable to this particular one to be equal to something. So then we are storing the actual value to the I and we are now comparing it. We are using AND to check if the bit at this position is 1, we need to check before we flip it, before we use XOR operator to flip it, because if we are not checking it, if it's actually 0 and we flip it to 1, that is not what we want, right? We want to check if it's actually 1, then we flip it to become 0. We are checking using the pointer that is pointing to the number. Once we dereference the number, it will be equal to that number it's pointing to, and we are using AND operator to do what? To AND it with 1. So once we AND it with 1, 1 and 1 is going to give us 1. If it gives us 1, definitely the AND operator is true and the next line gets evaluated. But if we check it and let's assume it's like this, the AND operator will evaluate to 0, because 0 and 1 is what? 0 and 1 is 0. The if statement will not get evaluated. Likewise, the statement under the if statement then will return, because we just want to leave it the way it is. But if it's actually 1, the if statement will get evaluated, because the AND operator will return 1, because 1 and 1 is 1, and the next statement gets evaluated. So in this particular statement, we are using XOR binary operator. XOR means that if the one, XOR works by checking if the 2 bits are of the same type. How does XOR works? XOR checks if the 2 bits are either 1 or 0, then it becomes 0. But in this case, our 2 bits are 1, so it becomes 0. And we are storing the result back to the variable num using the pointer ptr. Then our function gets returned. So now let's check. Let's comment this and check. Yes, our function is actually working right. In this exercise, we want to write a function that returns the value of a bit at a given index. This is the main function where the evaluation of our program starts. We start with declaration of an integer variable, and we are storing the return value of our function into the variable, and we are printing it in the next line. Into this function calling, we are passing 11 and 3. 11 is the actual value that we want to evaluate. 3 is the index of the value. This is our function. Now let's start by writing the content of our function. We start with declaration of an integer I, which we are going to use in our for loop. We are using loop because we want to iterate through every bit of our number. So we want to start from the very first one. Definitely our I should be 0, and while I is less than 32. We are using 32 because a byte consists of 8 bits. An integer number, which is 4 bytes, consists of 32 bits. Then we are incrementing our I. And for every iteration, we want to store every bit into this bit variable. Then let's declare bit variable. How do we store each bit into this bit variable? We can do that by right shifting our value at a particular index and compare the value using AND operator with 1. What does this mean? In the first iteration of the loop, when our I is still 0, 0 minus 31 is still 31. Definitely, we are right shifting the num in 31 places. Our num is 11, and we are right shifting it in 31 places. So it's going to shift out all these other values, leaving us with just the first one. Then all this one will be equal to the first value, which is 0. 0 and 1 is going to give us 0. Then 0 will get stored in the bits. So when 0 gets stored in the bit, we want to store the 0 into our binary array. Now let's declare the array. Because we have 32 bits, let's make the array of size 32. Now we want to store the value in our binary array. So at index I, which is 0, we want to store bits. So on the second iteration, when our I is equal to 1, 31 minus 1 will give us 30. Then we are shifting num in 30 places. The actual bit number of our value is 32. It's going to shift out all these 30 values, leaving us with just the first two. Out of these first two, it is only the second one that will get ANDed with 1. In 0 and 1 will give us 0, and 0 will get assigned to the bit, and the bit will get stored in binary array at index 1. It will continue as such till it reach here. I assume at here our I is 28. When our I is 28, 28 minus 31 will give us 3. Then we are right shifting the num by 3. All these 3 values will shift out, leaving us with all these other ones. Then we want to AND these other ones with 1. Definitely the 1 will just get ANDed with the last index, with the last value, which is 1. 1 and 1 will be equal to 1, and 1 will get assigned to bits. Then the bit will store 1 into the binary array at index 29, because our I is 29. We'll continue like that till we store all the bits into the binary array. After we stored all the bits into the binary array, then we'll need to end the binary array by assigning the null character to the last index. We have assigned the null character to the last index. Then we want to return the binary index, which is going to be 32 minus index. This means if we want to return the value of a bit at index 3, then 32 minus 3 is going to give us 29. Then we are returning the 29th value in binary array, which will be equal to 0. Index, which is third, means we want to return the third value from the right. The 1 will be the fourth, the other one will be the second, while 0 will be the third. Let's run our function. It's working perfectly. We are returned 0. Now let's change the value to 4 and see if it's going to return 1. It returns 1. Now let's change the value again to 2 to see if it's going to return this 1. It gets returned. With this, we've come to the end of our video. Thanks for watching. I'll see you in the next video.